Alright, so today, folks, we're going to be learning about factors that affect the rate of a reaction. So it turns out that if we look at all chemical reactions and examine the factors that affect how quickly they happen, we narrow it down to about 5 factors. And the first of those factors is the chemical nature of reactants. So it turns out that some substances just like to react with some other substances and don't like to react with others. That's just their chemical nature. You may remember in grade 10 talking about single displacement reactions and how there was an activity series that we needed to look at before we decided whether a reaction happened. And that had to do with the chemical nature of the species that are reacting. So be it electronegativities, could be just the bond angles, the molecular geometry. There are a bunch of different factors. A good example of this would be knowing that alkali metals and alkali earth metals such as magnesium will react fairly quickly with hydrochloric acid. We'll see some bubbles of hydrogen gas being produced. But if we were to take that same magnesium and put it in sodium hydroxide, we would see no reaction happen there. And that's just the nature of those materials and whether they interact or not. Okay, so essentially we can narrow that down to the unique chemical properties of the particular materials that are interacting. Okay, a second and very important factor is the ability for those reactant molecules to come into contact. In order for a reaction to happen, they have to be able to meet. And so the more readily that they can do that, the quicker the reaction will be. So in general, we say that the greater the surface area available for the reaction, the faster the reaction. So of course this applies primarily to cases where we are looking at solids. So I like to think about it in terms of building a bonfire. So if I'm building a bonfire, I usually want to start out with some high surface area materials, such as some paper, some kindling, things like that. If I were to try to begin a bonfire by using a big honkin' chunk of wood, that's just not going to work, and I'm going to have a hard time getting that fire going. And there are some really good reasons for that, and we're going to take a look at that in the next picture. So another good example is if I were to take that chunk of magnesium metal and plunk it into some HCl, and then I try to do the same with some magnesium powder. So let's look at the first case. So the first case is where I take that big honkin' chunk of magnesium metal and I place it in some hydrochloric acid. Now, of course, in hydrochloric acid, the H+ ions are going to start to float around freely, and they're going to try to attack the magnesium. But in that big chunk, the hydrogen ions can only attack the outer layer of magnesium atoms, and before they can reach the interior. So this interior part of the magnesium isn't interacting at all with the hydrogen ions, and that's going to slow that reaction down. If I were going to take the magnesium and grind it to a fine powder, then I break it down into chunks. I increase the surface area so that these hydrogen ions can attack from all sides. And so that's going to really speed up the rate of this reaction. Okay, the third factor affecting the rate of reactions, and this primarily affects aqueous solutions and solutions of gases, because we can change the concentrations of those. It's really difficult to change the concentration of a solid. It is what it is, and the same goes for liquids. But aqueous solutions, we can increase or decrease the number of moles that are dissolved in those solutions, and we can change the concentration of a gas by increasing or decreasing the pressure. So, as it turns out, the greater the concentration of the reactants, the faster that reaction will happen. And I like to think about it in the same way as if I'm traveling on the highway. If there are lots and lots of cars on the highway, there's a much greater likelihood of some kind of a collision happening than if there are very few to no other cars on that same highway. So I want to illustrate this for you a little bit better. Imagine that I have a beaker with some highly concentrated acid here, and you can tell that it's highly concentrated. I'm depicting this by showing lots and lots of dots representing acid molecules, or the ions that make up that acid molecule, floating around freely. and I were to compare that to a beaker full of a much more dilute solution of acid, and if I were to place in that a big honkin' chunk of magnesium or some other metal that's reactive with that acid, so you can imagine that because there are so many more molecules in a given volume of acid in this leftmost beaker here, that there are going to be many, many more opportunities for collisions to happen between the acid molecules and the magnesium metal, as opposed to my more dilutely concentrated acid. Just heard the bell there, that's great. Another good way to think about it is that wood will burn really, really well in air, fairly well, but if we were to take some pure oxygen and try to light that, get that wood burning, then we would find that we would be creating a fairly dangerous situation that would happen much more rapidly and violently.